Hey, so I'm going to be talking about CPython internals. My main point here today is that getting started with the internals of Python is both worthwhile and easy. So first I'm going to talk about the worthwhile part. So my contention here is that there's a dangerous gap between the high-level high-level concepts we use when we're doing Python and the mechanics of how your computer actually works. If you learn about internals, you can protect yourself from the bugs that live in that gap. So to demonstrate, I'll be giving you a couple examples where Python has really unexpected output, and then showing how peeking into the internals of your Python objects at the REPL can really clarify what's going on. First, I'll explain about the gap. So yeah, this is a visual representation of me using Python. Python is full of high-level concepts and features. It's what makes it fun to use. Like when you do a for loop, you don't have to worry about indices. When you do file I/O, you don't have to do, you don't have to close anything because you have context managers. The downside here is that you abstract away from how computers are actually doing things underneath the hood. What ends up happening is that you kind of explain things in terms of magic. Like when you learn about fundamental data structures like lists and dictionaries, people say things like, oh, a list can hold like any kind of data. It can go as long as you want. Dictionaries like remember the keys that you hand them, and they can fetch things later by name. And these are really useful metaphors for getting started, and they're easy for humans to understand, but they're not a good representation of what's actually going on. So the harsh reality is that Python is a program written in C. If you're unfamiliar, C is like a programming language from a much more brutal time. There's no context managers and stuff like that. You're just storing bytes of data at particular addresses in memory. It's not metaphorical. It's not magical. It's much closer to the underlying functionality that your hardware supports. Side note, I'm calling these memory addresses, but they're actually virtual memory addresses. There's like an OS layer there. We're not going directly to the hardware. Anyway, yeah, so this is the gap. On the one side, you have Python with its high-level, lovely abstractions, and then on the other side, you have C and the brutal reality of programming in C. So most of the time, it's perfectly fine to live in the magical realm of Python. However, when things stop making sense, being able to close that gap and really understand the internals can help you. So the first example is going to be dealing with the is operator. The is operator is supposed to take both arguments you give it and tell you whether they're the same thing. So when you compare it with 50, two variables assigned to 50, you're going to get true. It turns out if you do that with 500, you get false. This is kind of a WAT moment. A lot of people use is with one or two cases and feel like they know what's going on, and then something like this happens, and they feel like they're taking crazy pills. And it's hard to see as a user of Python why you would want these two cases to be treated differently. They're both integers. Why is one getting treated one way and another a different way? Is there a high-level reason for why this happens? It turns out no, but there's a low-level reason. Python recycles common immutable objects for the sake of conserving memory. It's called interning. So when we're using A equals 50 and B equals 50, they're actually getting pointed to the exact same object. The reason that this works is that if you have an immutable object, the content is the same. So you don't need dozens of copies of the integer 50. You can just use one. It's never going to change. That's the logic anyway. Usually, it's not a problem. So to go back to our original example, when we're doing A is 50 and B is 50, that's getting assigned to this one object. In the second case, A is 500, that's going to its own object. B is 500, that's going to a separate object. And that's why they don't end up being the same. So far I've just been gossiping about how this works, but that's not how you want to go about coding. It's not how you want to live your life. So how about actually dig in and show this at the REPL? So how we're going to do this is we're going to be reading directly from memory that Python is using. So this isn't going to be Python spoon feeding us the data. It's going to be going directly to a memory address and then reading what's there. You can think about it like we're archaeologists kind of following up behind Python like it's some ancient civilization and just reading their ancient runes. It's like Indiana Jones in the Temple of Python, let's say. So how are we going to do this? We're going to use two tools mainly. We're going to use the ID function. It's a built-in. That's going to tell us where in memory the object that you hand it, where that object lives. This is CPython specific. You can always treat it like an identity, but we're going to use it specifically to find where in memory it is. So the ctypes library is a second tool. That's going to allow us to read the bytes that Python has written into a format that the REPL will understand. It's going to be kind of a Rosetta Stone between C and Python. So yeah, back to the mission at hand. We want to be able to break open these integers and sort of see what's going on inside to help us understand the earlier scenario. So we have the insides of an integer up right now. It turns out it's just 3 numbers glued together. In C, that's a struct. 3 C longs. So this is nice because the perception is that Python internals are really complicated. It's kind of fun to break it open and just find that there's 3 moving parts here. The last 2 are pretty self-explanatory. So the value, obviously, that's going to be 50 or 500 in our case. The address of the integer type, that's going to be where in memory the type for this instance lives. And then the reference count is really the one that's worth talking about. So reference counting is how Python does its garbage collection. The reference count is the number of variables that point to this particular object. So if you have A and B pointing to this object, you're going to have a reference count of 2. As you delete variables, those will go away and you can garbage collect. So the reference count goes to 0, this whole object goes away. So that's all there is to an instance of an integer. You know everything there is to know about integer instances now. No metaphors. In case you're curious, this is what the underlying C code looks like. The reference count and the type address are in that PyObject head, and then there's the value at the end. Only reason I bring this up is just because it's nice to see sometimes that, again, it's not that complicated. It's just like 3 lines or 4 lines of C code. So let's just take this for a test drive and see that this is working. So first entry, reference counting. We're going to take the ID of A and plug that into the ctypes function from address and read that out as a long. That's what's happening here in this slide. And we get out a 1, which is what you'd want because you've just assigned 1 variable to that object. And then try assigning another variable. You get 2. It seems like it's working. So second entry, the type address, we can read that out the same way, except we're just going to move forward 8 bytes. So again, the ID tells you where in memory to go, and then you can just move forward 8 bytes at a time to get the subsequent entries. So we get some long address here, and if we look up where the integer type lives, it's actually the exact same place, so we can verify now that we've got the type address in the second slot. And then finally, we get the value, and we were looking at 500. That was our particular integer we were looking at, and you get 500 out, so we've covered all our bases. So now let's go back to the case we were trying to explain. In the case of 50, we can check to see if the IDs are the same for A and B, and they are. So we have one object in question here, which gets us most of the way to verifying that interning is actually what's going on here. And then if we look at the first entry, the reference count, we can see that we've got 8. So this is an object that is used not only by our above variables, but throughout the Python core libraries, elsewhere in code. So this is definitely an interned object. And then if we look at the second case, we can, again, compare A and B and find they're not the same object. So we've got 2 separate 500 integer objects. Looking at the address, reading out, the first entry, the reference count from address, we're going to get 1 for each. So these are two separate objects, and they each have a reference count of 1. They're not being interned or anything. So the whole point of this was just to show that there are instances where if you have a really confusing chunk of Python, going underneath the covers can really help explain what's going on. So I'm going to do one more example. So in this case, we're going to be building an array in kind of a silly way from 0 to just under 1 million. So even though we're doing it in a silly way, it executes in about 1/10 of a second. This is sort of the time frame that you'd want for a program. It turns out if you switch gears and insert from the other direction, so not appending but inserting at the beginning, what you get is about 4-minute execution time. So again, this is like a WAT scenario. I see a lot of people shaking their heads. If you're involved in any kind of scientific computing, that's a big no-no, I'm sure. So if you want to do, if you do the math, it's about 2,000 times slower. Coming from a high-level Python perspective, though, it's hard to point at exactly what is going wrong here. Looking at the Python 3 API, there's actually no guidance on inserting at the beginning or the end. They're kind of treated equally. So again, it turns out it's a low-level detail that you need to know here. It's a fundamental limitation of C arrays. So we're going to take a simple example here just to illustrate. Say we want to insert an entry into the middle of some array we've already got going. Ideally, you would just want to leave everything else the same and just stick your new element in there. But if you think about it, these are memory addresses. You can't just create a new memory address to stick in the middle of your array. That's OS territory. So what ends up happening is that you have to move every subsequent element down, which means you're rewriting everything that comes after that insert. So it's like a cascade of rewrites that you're causing. So again, this is just me gossiping about this. We should really just show this at the REPL. So to do that, we're going to have to butcher up a list this time. there's a lot in common with how an integer works. The reference count, the address of the type, the length, that's kind of analogous to the integer case. The last two, the new entries, these are going to be with respect to the array of items. So we have the address in memory of that array of items, and we have the number of spaces that we've allocated for that array. It's different than the length because Python usually over-allocates, so you don't have to do that constantly when you're adding items. Maybe this is a little more helpful. We have this contiguous block in memory, which shows you the values that we were looking at in the last slide. And then you have separately this other contiguous block in memory that just has the addresses of the items in your array, or items in your list, rather. And it's important to note these aren't the actual items because they could be giant classes or collections or something. These are just the addresses so you can find them from this array. Again, the underlying C code is not that complicated. So it's just something nice to note. So I'm going to be using a little helper function that is just going to be spitting out this array of items. It's a little big to put on a slide, but I'm just going to put it up there for the sake of fairness. The only line you really need to pay attention to is this last one. All I'm doing is for each entry in this item array, I'm spitting out which entry it is, the address in that entry, and then what it points to, the actual value. So for a simple list, we've got each entry, we've got the pointer or address, and then the actual value there. Simple enough. And if you append something, you can look at that array in memory and see what's changed. It's highlighted in green. It's really only the last entry there. But when you insert, you can see how entry 0 suddenly becomes this new thing. Entry 1 subsequently becomes a new thing. They all have changed. And what that means is that instead of a million writes where you just append, you're actually doing one rewrite for the first one. You're doing 2 because now you've got 2 things to move, 3, and so on and so on. And if you take that summation, it's actually about 500 billion rewrites, which makes sense that it would take 4 minutes. Yeah, so again, this was just an illustration of how knowing a little bit about internals can save you from some nasty bugs. And if you're interested in learning more, I'm going to be putting up a guide pretty soon about how not only integers and lists are laid out, but also dictionaries, all the other common data types. And then here are 2 blog posts that I would highly recommend. Brandon Rhodes' talk, I've borrowed a bit of examples from there, and I think it's great for learning how these things really work, not in metaphor, but actual mechanics. Thank you very much. Sure.
That's very interesting. Good job. Are you running this on the Mac, or are you running the example of inserting from the beginning or inserting from the end? Mm-hmm. Are you running that on the Mac?
Yeah, that was just running on my MacBook Pro.
On OS X.
Yeah.
Okay. Cool. That's OS X has one of the most complicated memory manager in the world. It's materially different than Linux and Windows. And I was thinking that maybe this exact problem might have been addressed by the kernel developers at Apple. They were thinking about it. You can read some of their publication journal articles. It turns out that you can they have an abstraction layer of memory address remappings. So they can see a pattern of what you're trying to do and be like, oh, this is an insert. Let's just pretend it's over here when it's actually over there.
Wow.
But then Python doesn't know that so Python's the application sees a contiguous block of memory, But
Yeah.
the actual like physical allocation of charge capacitance in the actual RAM module has been remapped.
Wow. So I realized I forgot to repeat the question. But the question was I running this on OS X? I was. And so there's an interesting project, I guess, over at Apple to see if they could actually just do work on the virtual memory addresses to make this kind of thing faster. It was really interesting. Thanks. And I am totally out of time, so we're going to stop there. Thanks.